Okay. We've now moved on to phase 3 of the 213 semester. Whoa, we're way past halfway. Test 1 was about motion, linear. Test 2, motion, circular. Test 3 is going to be about a lot of other things, not necessarily motion, but filling in a lot of the gaps. In our adventure in physics, we've come up with the idea of force, and which is in kilograms, meters per second, which is just mass times acceleration. And we have the idea of area, which is in meters squared, which is just, you could think of it as x squared or whatever, length times width, stuff like that. And what we're going to do is we're going to talk about a new concept called pressure. Now, pressure, which we will go with P, is force divided by area. So one of the units that you typically hear are pounds per square inch. What we're going to do is talk about the metric system version. And if we put this together, we get newtons per square meter. Newtons per square meter is the common units for pressure. Now, there are, just as we have kilogram meter per second is a newton per meter squared, they have their own term for that. 1 newton per meter squared is equal to 1 PA, and PA stands for Pascal or Pascal. I don't care about the spelling, with the E, without the E, doesn't matter. And what we're most familiar with is air pressure. The air is pushing down on us, and 1.013 times 10 to the 5th Pascal is equal to 1 atmosphere. Atmosphere of pressure. When you think about pressure, we have, don't worry, you're very nice shoes. So if I had to inflict pain on your foot, what I could do is I could just take my foot and stand down. That would hurt. Now, how would I make that hurt more? Well, it's already hurt. But as a professor, what's better than pain for me? So how would I do that? How would I hurt your foot more? There are 2 ways that I can do it. So think about pressure. What way could you increase the pressure of my foot on your foot? Increase the force. So instead of just doing this, I just go and do that. That would really hurt. Or decrease area. So instead of taking my foot and hitting his foot with it, I take like a train spike, put the spike on his foot, which now the contact point of the spike is a lot less than what my foot would be, and then hit it with the same force. And you probably get punctured out of it. So with pressure, you can either increase the force on something or take the same force and decrease the area. And when you think about it, kind of when I was like a little kid, my mom was driving, and I said it, she just like looked up and looked back. When you look up into the sky, there's nothing keeping the atmosphere in. It's just space. Now granted, the gravity is holding all that air down, and all that air is like on top of us. So the higher we go, the less atmosphere. Think about like, if you've got one blanket on you feel a certain amount of pressure. You put 10 blankets on you feel a little bit more. You put 100 blankets on you, now you're getting pressure. So the air is pushing down on us. We have a certain amount of mass above us, and it's all pushing down. As an example, we have to now introduce an element. I may have said this before. A lot of times, now one of the questions obviously that people will ask is, do I have to memorize 1.013 times 10 to the 5th pascals per atmosphere? No. Oh my goodness. Why do I memorize it? Because I had to say it 50 billion times, and eventually it just burns into your brain. But for a lot of the materials that we use, I'm going to give you the basic stuff, such as the idea of density. Materials have different densities, and density is known as rho. Rho, or you could think of it as, it's a Greek R. A little, kind of like a P, little P, but with a little squiggly at the end. And this is mass over volume. Density volume density is the common word for volume density. Most everyone, when they hear density, and I wouldn't fault you if you thought this way, because it's probably the expected way. Volume density is normal density, and density is the mass per unit volume. There are two other types. You won't be tested on, but I'm just going to tell it to you now so that if I say it at a later time, you understand. There is area density and linear density. Area density is commonly referred to as sigma, and that is mass over area. Linear density is lambda, and that is M over L. Or sometimes I write M over big L. Either one. It's length. This will be used with fluids, anything dealing with volume, stuff like that. Area density, as in like, if I wanted to know what's the total mass of the tiles on the floor, what I would do is I would weigh one tile, and then really the tile is 1 square foot, because I've actually measured it before. And so if I know there's so many grams per square foot and the room has so many square feet, I could get the mass of the floor. sigma and lambda are frequently used when it's experimentally advantageous to use those values, such as lambda we're going to be using for sound. Lambda, think of guitar strings. What's easier to measure on a guitar string? Its volume or its length? You can measure its length, just get a yardstick, meter stick, whatever, and you can measure its length. To measure its volume, it's going to get a little bit more tricky. It is experimentally easier to measure the length, and so guitar strings, so many grams per meter, it's just an easier way to measure things. Area density is almost, we won't be using. But linear density we will use in a little bit, and density is our common, we'll be using that frequently right now. Some common densities, I just remember this. Density of water is 1,000 kilograms per cubic meter. That's pretty much like the universal constant for, common densities, it's water. In, there's a whole list of densities. There's all sorts of elements. But to let you know of a, I'm too lazy to, I'm not a botanist, I'm not a biologist, I'm not an organic chemist. I don't take the time to memorize 5 billion irrelevant bits of information. So what I do is I just make up my own element. And if you hear a word called rebellium, it's a fictitious element or substance. Who made it up? I made it up. It's my invention. If I invent an element or discover an element, I will name it rebellium. Rebellium has whatever density I want. Rebellium will have, it'll either be a gas, liquid, solid, doesn't matter. It's whatever I need it to be, because I'm too lazy to look it up. It's not the number that interests me, it's the concept. So let's do a basic thing. Let's say you have a cylinder and the mass of the cylinder is 5,000 kilograms. The height of the cylinder is 4 meters, and the radius of the cylinder is 1 meter. And this is made of rebellium. The density of rebellium is what? Now I will tell you, time to have a little story time. One particular summer, the class demanded in the test that I give it the equation to measure the volume of a cylinder. I protested. My reason was, you are a human. You are a college individual. You should have basic geometric information in your skull. And then they repeatedly said, but we're dumb, we don't understand anything. They were a particularly special group, I must admit. So I said, fine, we're gonna do a deal. I'll give you the equation, but if I ask my doctor to give me the volume of a cylinder and she answers it correctly, I will never give this equation to another class again. It will not be in the equation sheet. And they accepted it happily because they got what they wanted. And then I went to my doctor, and I said, can I ask you a question? She said, of course. And I said, well, what's the volume of a cylinder? And she goes, pi r squared H? Now granted, she did say it as a question, but she did get it correct. So congratulations. Basic cylinder, pi r squared h. Sphere, volume, 4/3, pi r cubed. Volume of a cube, length squared, some basic rectangular object, length times width times height. All these basic geometric shapes you're going to have to know. Now, if I was cruel, I would expect you guys to know a volume of a pyramid, but I'm not. So, and it would never show up on a test. So the weird, complex volume of a donut, stuff like that, I don't expect you to know, we're not going to work with. But cylinder, cube, and sphere, you gotta know. You're a human. You have a 3-pound gland between your ears. I suggest you use it. So stuff like this, you need to just know on your own. So the volume of rebellium, since it is a cylinder, is pi r squared h. So the density is mass over pi r squared h, or 5,000 times pi 1 squared times 4. So 1250 divided by pi, 397.9 kilograms per cubic meter. That's the density of rebellium, that sample of rebellium. Next question. That's the density, yeah. What else would it be? Okay. Next question. What's the pressure of the cylinder on the ground? Now pressure is force divided, force divided by area. What's the force? Mass times acceleration, or mass times gravity. The area is the pi r squared, the base of the object. So this becomes, I've got 5,000 kilograms times 10 divided by pi 1 squared. And I get 15,915 newtons per square meter, or pascals. And we could rewrite this as, take this, multiply it by 1 atmosphere per 1.013 times 10 to the 5th newtons per meter squared. And we get 0.157 atmospheres. So the pressure contributed by the cylinder on the ground is approximately about 1/8 of an atmosphere, 1/7 of an atmosphere, something like that. Now let's look at something that's interesting. If if I say that the pressure is rho GH, let's just say I magically pulled it out of the air, you would see that the density of the material, 397.9 times 10 times its height, 4, gives me 15,916 newtons per meter squared. It's off by 1, but there's rounding involved, a little bit of bit rot. So it's close enough to say that they're identical. Well, that's rather interesting. If I take the density of material, divide it by gravity, and then multiply it by the height above the surface, I get the same pressure that I do over here. Well, let's figure this out. Pressure is force divided by area. Well, what's the force? mg. And I'm going to keep area. Well, what's mass? Density is mass over volume. Kilograms per cubic meter. So what I can rewrite this as is rho V is equal to m. This equation right here, density is mass over volume. My nickname for it is the Swiss Army knife of equations. This, and that. The three variants of density I use on a regular, well, not on a regular research basis, but in terms of problems involving fluids and sound, all sorts of stuff. These three equations, when in doubt, see if you could throw that into the mix. I've got a mass, but I don't know, well, I do know what it is, but what I'm doing is I'm playing with it in general terms. Mass is rho times V. So this becomes rho VG over area. And what's the volume of any object? The volume of any object is the base times its height. So pressure becomes PAHG over A. And that gives me rho GH. So what I've done is, you could take the cylinder, figure its mass out, multiply it by gravity, divide by the area of the base, or you could take the density of material, divide and multiply it by gravity times its height, and you get the same thing, which I've shown here equaling here. So when we're outside, now granted, it's not necessarily true because the density of air changes as a height. So if I have a height of, if I want to know what's the pressure of air for, I don't know, 1,000 meters above me, I don't necessarily have to compute my area or the area that I'm interested in. All I have to do is know the height, know the gravity, know the density of air. Density of air, if I remember it offhand, so if I have a kilometer of air pushing down on me of uniform density, I think the density of air is 0.16,
kilograms per cubic meter. If that's different, doesn't matter, I can add on that later. Times 10 times 1,000. I get 1,600 newtons per cubic meter. So the air above us can push down. Now what I'm gonna do, I mean, it may be that the density is something different, but what I'm gonna ask now is, if you are, oh, this is the better one. If you are "30 meters underwater," what is the pressure contribution due to the water? So now we've got a tool that we can use. P equals rho GH. The density of the fluid is the water, or 1,000. G is 10. H is 30. Or 3 times 10 to the 5th newtons per meter squared. Now if you take this and multiply it by 1 atmosphere per 1.013 times 10 to the 5th newtons per meter squared, you get roughly 3 atmospheres. So rule of thumb, just a saying, for every 10 meters of water above you, there is 1 atmosphere of additional pressure. So if you're at 10 meters underwater, there's 1 atmosphere of water pressure on top of you. If it's 20, it's 2, etc. Now, one of the things that I use as examples for working with fluids is, in my senior year in high school, I learned how to scuba dive. And throughout college and a bit of grad school, I would go to Florida. My family lived on Guam and Hawaii, and I'd go out there. My brother, his senior year of high school was spent at JFK High in Agana, Guam. And he was able to, every day at 1 o'clock, walk out of the high school, go to the beach, and scuba dive for the rest of the day. And it was like, he lived the crazy life. So you got to learn about how pressure affects you, and it does have certain biological effects. One of the things about pressure is the pressure on your body, the pressure of the water and the fluids. At normal air pressure, nitrogen only slightly enters the bloodstream through your lungs. As you increase the pressure, that probability of nitrogen entering your blood increases. At 10 meters underwater, it's not that big of a deal. At 20 to 30 to 40, then it becomes a bigger deal. If you go deep enough, you have to change the quality of your gas that you breathe. You have to switch it to a higher percentage of oxygen, reduce nitrogen, and stuff like that. Now, with this pressure, we have to remember that pressure due to water is a partial pressure. When you're underneath the water, looking around at the fish, you've got so many meters of water on top of you, but you also have all of the atmosphere pushing down on top of you as well. The total pressure is atmospheric pressure plus the pressure of the water. So at 10 meters, pressure total is 1 for atmosphere, 1 for the water, or 2 atmospheres. The total pressure on your body at 10 meters is 2 atmospheres. At 20 meters and 30 meters, it's 1 plus 2, 1 plus 3, and so on. So there is an additional pressure. If you are at sea level, if you're exactly at the level of the water, you're at 1 atmosphere. You have no water above you but air. So if you go 10 meters down, you have 10 meters of water and the atmosphere pushing down on you. So you have to take both into account. So there's a partial pressure and a total pressure. With these multiple pressures, there's also something called gauge pressure. The gauge pressure is similar to the pressure of the water. Where does the gauge pressure, where is it commonly used? Well, most everyone has a car. Most everyone checks the air pressure on their tires. Let's say you read 2 atmospheres on your tire gauge. That is a partial pressure. What the gauge is reading is the overpressure. The pressure of the tire that goes over your standard atmospheric pressure. So for a gauge pressure, the total pressure is the atmospheric pressure plus the gauge pressure. So total pressure for this would be 1 plus 2, which is equal to 3. So remember that there is a difference, there is something called partial pressure. This, the pressure of the cylinder on the ground, that was a partial pressure. So the pressure of the cylinder on the ground was 0.157 atmospheres. The total pressure is atmospheric pressure plus the pressure of the cylinder. So it is now 1 plus 0.157 or 1.157 atmospheres. And so that is the total pressure on the surface because of the cylinder and the atmosphere. All right. Thinking if there's another thing that we need to know about pressure. I think we're good. If there's anything else, I'll cover it later. Now, with these fluids, you can do a lot of different things. The pressure, we kind of figure about pushing down on things, but there's something that we know on a regular basis, or we've experienced on a regular basis, and that is buoyant force. It's the force of the fluid pushing an object out of the fluid. Now, one of the best, before we went scuba diving, went to Guam and scuba dived for a year or so. We had a pool in the back of our house, and we used to play the game called Submarine. What we did is, on the ladder in the deep end, what we did is we took a paint bucket, those big buckets, turned it upside down. Both of us would pull down on it so it would be full of air. We'd push it underneath the ladder, let it go so it would rest up against the ladder, and then we could take our heads and stick it in the paint bucket, and we'd be able to breathe underwater. So that's how we called it Submarine. And then once we got lightheaded, because the air was now full of carbon dioxide after a while, we'd take the bucket out, we'd refill it, and then we'd do it again. So one of the things that we notice is if you just had that bucket completely out of water, it's upside down, you're just holding it above the water, well, what do you feel? Well, all you feel is the mass of the bucket pulling down. Well, what if you partially submerge it? What do you feel? Well, you feel a force that's up. That bucket wants to get out of the water in a bad way. What's really happening is that the water, you're displacing the water to the sides, and that water is trying to force its way back in. That force up is the buoyant force. If you pull it down even further, what do you notice about the bucket? The force, I'm sure everybody in the room has tried to submerge a bucket in water. If you submerge the bucket, you feel a greater force. That force increases. But what you notice is once submerged, this force plateaus. That once you submerge it, that force linearly increases. Once this volume reaches a certain point, i.e. reaches the point when it's fully submerged, that force doesn't increase. So my brother and I, if we were able to get that bucket underwater, we were good to go. If we couldn't get it underwater, we didn't have the force necessary to completely submerge it. But once we got it underwater, we were able to move it around, because if we were able to overcome that maximum force, we could hold it underwater. This buoyant force, which we typically call F sub B, is rho V G. And typically I write V sub D. This rho is the density of fluid displaced. If you take that bucket into a pool of water and you pull that bucket down, upside down, you're displacing water. If you've got, this is highly frowned upon, if you've got a big vat of mercury, which is poisonous by the way, but if you pulled down that bucket, you would be displacing mercury. This V sub D is the volume of displacement. Here, the volume of displacement is equal to 0. So if the volume of displacement is equal to 0, then the buoyant force is equal to 0. Here, the volume of displacement increases. And here, the volume of displacement is equal to the total volume. So if you're dealing with a partial submersion, you have to know the volume of displacement. If it's completely submerged, then you can get away with knowing the total volume of the object. And then G is just gravity. The 10 meters per second per second. So if we had a massless 0.1 cubic meter bucket what is the minimum force required to submerge the bucket? So here's our bucket. We're going to use a point because I'm tired of drawing buckets. And the buoyant force is up. This force is the force that my brother and I have to do. The pull, force of the pull. And I have to find out the minimum force of the pull necessary in order to pull the bucket down. That means that the minimum force necessary to pull it is when it's in translational equilibrium once it's fully underneath water. The sum of the forces is equal to 0. And so this gives you F sub B minus F sub pull. So F sub pull is equal to F sub B. So F sub pull is rho Vg. Rho is the density of the fluid being displaced or water. So 1,000. V is the volume being displaced, or 0.1. G is gravity, or 10. So we have to pull with 1,000 newtons of force down to get this bucket completely underwater. If we use less than 900 or less than 1,000, it won't sink. If we use more than 1,000, it will. If we use exactly 1,000, we can easily enter it into the pool. And that brings us to three special phrases. That is positively buoyant, neutrally buoyant, or actually, hold on, whoa. Change. Let me rewrite it. Okay, hold on. Neutrally buoyant. I gotta get the order right. Positively buoyant. And negatively buoyant. When we were on Guam, we started doing something. When I left, my brother perfected the art. And then when I came back a year later, it was amazing. There are, on Guam, there are these coral reefs. And coral reefs, you got all sorts of fish and stuff. And the fish that we would hunt for we wouldn't hunt, but we would look for it, are pufferfish. These are the little, in the Atlantic, their spines are a little bit sharper. In the Pacific, they're kind of just prickly and annoying. With gloves, you can handle them. So, pufferfish, their defense mechanism is when you frighten them or threaten them, they just suck in water. They've got a special water bladder inside them, and they blow up like a beach ball. They're probably the size of a grapefruit when all blown up, and their little spines stick out. So if you surprise a pufferfish, it sucks in a lot of water and it looks like a big sphere. Well, it's filled with the fluid that it's displacing. So it has a particular mass times gravity coming down, and it displaces a certain volume, so its buoyant force is going up. But since it's effectively displacing the water with water, the sum of the forces, which is positive FB minus mg, is equal to 0. The buoyant force is approximately equal to that of the force of the water and the fish pulling down. Now this is the fun part. What my brother and I would do, now when the fish is basically a sphere, they can't swim for anything. Swimming ability just goes out the door. That makes them easily catchable. So you run up to them, well not run, you flipper up to them and you grab them. And my brother would, or me, would handle the fish and turn it face down. And then the other one would take the air regulator out of their mouths, put the air regulator up to the mouth of the pufferfish and hit the manual air blow button, and we would blow air into this fish. We would displace all the water in the fish with air. This fish now, it's still displacing the same amount of fluid. So the buoyant force remains the same. Same volume, same fluid displaced, same gravity, but the mass of the water inside the fish and the fish itself goes way down because we've displaced all the water in the fish. So its effective mass is reduced. So this big FB minus little mg means that the sum of the forces is greater than 0. If the forces balance and it floats, just goes side to side at most, but doesn't go up or down, it's neutrally buoyant. So now that we've displaced all the water in this fish, we let it go. Let it be free. So you've got that huge buoyant force up, very little mass force down, and that thing just whoop shoots up. Now literally this ceiling is about what, 20-30 feet? So this fish, effectively, we're not that deep. We release the fish and it just goes like a balloon up to the surface. Now, when it gets to the top of the, when it gets to the surface of the water, it's a little tired. And that thing deflates like an airbag. It just goes, like it just releases. So now we've got this flatfish at the top. What has happened is it's decreased its volume it has somewhat of its mg, the mass of the fish doesn't change. So what happens is that the buoyant force is really tiny and the mass of the fish pulling it down is greater than that. So the sum of the forces is less than 0. If it's positively buoyant, it rises. If it's negatively buoyant, it descends. So we fill this poor fish up, we release it, it goes up to the surface, it releases itself as it's going up and at the surface. It's tired, and what it does is it just floats right back down to us, where we're waiting for it. And this thing would go on for a good half hour, and we would fill that fish up, throw it up in the air or in the water, it'd go to the surface, deflate, come back down, we'd catch it, and we'd do it again and again and again. The thing was positively buoyant and it was positively entertaining. But it's a great story in terms of understanding positive, negative, and neutral buoyancy. As another bit of the story, my brother at he was a Florida State marine biology major in an organic chemistry class, and he just got up and said, "I hate this." Left the class, dropped out of school, went to Costa Rica, became a professional scuba diver, and they had pufferfish off the coast of Costa Rica. And what he would do is basically every day take the diver tourists out to the reef, and they would find these poor pufferfish and blow them up and entertain the divers. Well, he told me later that what happens is the fish just sits there and goes, "I am not going to be your plaything. I refuse." And they don't blow up. And if they don't blow up, you can't pump them up full of air, and then it's not entertaining. And I said, "Well, what did you have to do?" And he said, "Well, we got around it, because what you do is," they weren't harmed, they were annoyed, "you take your fingers and you put them over their eyes, and then you just shake them." And that gets them frightened enough where they blow up, and then you can replace them with air and send them up to the surface. And so it's a great demonstration. And doesn't it explain more about who I am? I think it does. But in the end, it's a great lesson about taking physics and using a real world situation with it and understanding what goes on. The important about buoyancy problems is identifying all of your forces. So, as an example, water, balloon, line, ground. Everything is massless except for the fluid. The object is hollow, there's nothing inside. So hollow, no gas inside, massless. And I want to know, what is the tension in the string? The string is holding this sphere, hollow massless sphere underwater. The volume is 1 cubic meter. It's submerged, so I know that the volume of displacement is equal to the total volume. So the forces are buoyant force up, tension down. And I know that the sum of the forces is equal to 0. How do I know this? The balloon doesn't go up or down. It's neutrally buoyant. FB minus T, so T is equal to FB, which is equal to rho VG, which is equal to 1,000 times 1 times 10, or 10,000 newtons. So that's an easy way to calculate tension. If you know the thing is massless, you know there's no oxygen inside, it's just buoyant force up and tension down. Now let's change it a little bit. Still underwater. Still has a tension pulling down. It is hollow, no gas inside, shell has a mass of 100 kilograms. So the volume is still 1 cubic meter. The shell has a mass of 100 kilograms. Once again, calculate the tension in the string. Well, it's still not rising or falling, so the sum of the forces is equal to 0. Now we've got 3 forces. We've got the buoyant force up, we've got tension down, and we've got the mass of the shell and gravity pulling down as well. Because that shell has mass, it has to have a little bit of pull heading down. So this is FB minus T minus mg, or T is equal to FB minus mg, rho VG minus mg, or 1,000 times 1 times 10 minus 100 times 10, or 9,000 newtons. So we're down to 9,000 newtons. Now let's say that we have hollow 1 cubic meter sphere, the mass of the shell is 100 kilograms. The density of the inside gas is equal to 0.1 kilograms per cubic meter. Basically the density, effectively the density of air. Or if it isn't, it's just some gas inside. Just call it rebellion gas. So once again, water, sphere, string. What's the tension? It does have a gas inside. So what we do is we have the buoyant force. The shell displaces a fluid. So we have a buoyant force pulling up. We have tension pulling down. We have the mass of the shell and gravity pulling down. And we have, these are all attached, we have the mass of the gas times gravity pulling down. So now we have 4 forces pulling down. You've got to consider the fact that the gas inside has a mass, the shell has a mass, it displaces, so there's a buoyant force, and there's tension. Well, let's figure this out. Sum of the forces is equal to 0, which is equal to buoyant force minus tension minus mass of the shell times gravity minus mass of the gas times gravity. So the tension is equal to buoyant force minus this minus that. Now I didn't give you the mass of the gas inside. Well, this is where we get our Swiss Army knife equation and play with it. Density is mass divided by volume. So mass is density times volume. I know the density of the gas and I know the volume of the gas. I can figure this out. So this becomes FB minus MSG minus rho of the gas VG. This buoyant force is density of water VG. So this becomes gravity, density of water volume, minus mass of the shell, minus density of the gas times volume. So you may now plug and chug. Gravity 10, density of the water 1000, volume is 1, mass of the shell is 100, density of the gas 0.1, volume 1. Now, the lesson for all of this, because the number that we're going to get is 8,999 newtons. It's very close to this. When you're displacing fluids with other fluids, where the density of the fluid displaced is much greater than the density of the fluid doing the displacing. I don't know, the grammar's horrible on that. Let me explain it verbally. When you've got a density, the fluid has a heavy density and you're gonna displace it. What are you gonna displace it with? Oh, this light stuff. Either a vacuum or a gas. If you're displacing a liquid with a gas, you may ignore the mass of the less dense fluid. So if you're displacing water with helium, you could ignore the mass of the helium because helium has a very small density. Water is 1,000 kilograms per cubic meter. Another reason why I say you're allowed to disregard the small stuff is you guys have error in your lab of like 25% at least. And in lab, an error less than 10 is awesome. You've got an error of less than 10%, we're happy with you. This, we're off by 1 Newton per 9,000. That's a little bit more than 1/100th of 1%. Don't sweat that. That's not a big deal. So the small stuff you can effectively eliminate. And there are, on Blackboard are the new problem sets, and you guys can start working on it. So if you've got displacing water with a gas, you could ignore the gas. If you're displacing air with helium, now you've got a problem that you need to work on. Let's say in this last example, water, hollow, I won't need to know the tension. The mass of the shell is 100 kilograms. It's filled with a gas. The density of the gas is 400 kilograms per cubic meter. In order to do this, now you do have to keep track of this density. The setup is the same exact thing as this. So we end up with the tension equaling gravity, rho water V minus ms minus rho GV. This becomes 10, 1,000 times 1 minus 100 minus 400 times 1, which now makes it 5,000 newtons. That is appreciably different than 9,000. So if you're replacing a fluid with another fluid of comparable density, what does that mean? I would say if the density of the fluid doing the replacing, trying to think of how, like density of water is 1,000. I really wouldn't care. I wouldn't really think about the material unless the density of the fluid displacing water had a density greater than 10 kilograms per cubic meter. So if it's greater than 1% of the density being replaced, of the fluid being displaced, then I would care about it. But helium displacing water is irrelevant. That's like vacuum. That really doesn't matter. All right, we're gonna continue on with more fluids on Thursday. Problem sets are out. Congratulations, I passed by the lab at 8 a.m. on Monday. You guys, some of you were there and you were coherent, so I am pleased with that. See you guys on Thursday. Thursday, Friday, something like that.